Hello everyone, I'm Anish from EC department. We all write Verilog code and other hardware description languages, but FPGA doesn't know how to execute those Verilog codes. It only executes what is present in the hardware. So it is very important to know what is present in the hardware in order to write more efficient Verilog codes or hardware description languages. The board you are looking at on the screen is PINC Z2 board, a monolithic system on chip which is located under the heatsink. This single silicon die has two parts. One is PS and then the other part is PL. And this PL part is known as programmable logic, which is also known as FPGA, field programmable gate array. And the PS part contains dual ARM A9 cores. In this video, we'll be looking into what hardware is present in this PL part. Before diving deep into the PL part, let us look at how an ice cream is made. At first, we have the base cone, and on top of it, we place the several ingredients. Depending on the interests of each individual, the quantity of each ingredient may vary to get the perfect ice cream for them. In the similar manner, FPGA is a column-based architecture where we are having all these ingredients. Depending upon the each application, the quantity of each ingredient is varied, and we place the corresponding ingredient in the column. Each column contains one specific ingredient, as you can see here. Suppose if the specific application requires many logic functions to be implemented, then you will be having more logic which corresponds to SLICEL. Suppose if some application demands more multiply and accumulate units, example for signal processing, then in that case we will be using DSP. And ASMBL is known as Advanced Silicon Modular Block Architecture. We all think the combinational logic is implemented in the form of gates in the FPGA. But in reality, all the combinational logic is implemented in the form of LUTs. A LUT is a lookup table which is made up of SRAM cells. Suppose if I give 0, 0 as the input, then whatever the bit present in this SRAM cell, it will be coming as the output. And if I give 0, 1, then the bit present in the second SRAM cell will be coming out as the output. Suppose if I give 1, 0 as the input, then the bit in the third SRAM cell will be coming out as the output. Similarly, for 1, 1, the bit present in the fourth SRAM cell will be coming out as the output. Suppose if I want to implement a basic AND gate, then I need to put for 0, 0, it's 0, 0, 1, 0, 1, 0, 0, and 1, 1, it's 1. So depending on the A and B, which you give as the input, the corresponding output will be coming. So basically, by using a 2-input lookup table, we can implement any 2-input Boolean function. Suppose if I want to implement a 3-input LUT using 2-input LUT, I can do it by using a mux. If I connect the first output and the second output of the 2-input LUT to a mux, and then if I give the selection line to other input C, and if you have A here and B here, by putting the corresponding bits in these SRAM cells inside the LUTs, we can get a 3-input Boolean function as the output. For a 2-input LUT, we'll be having 4 memory cells inside the lookup table. Similarly, for a 3-input LUT, we'll be having 2 power 3 SRAM cells inside the lookup tables, 4 here and 4 here. Similarly, we can implement any input Boolean functions using these lookup tables. So I can use a 2-input LUT to implement any 2-input Boolean function. It can be AND, NAND, NOR, OR. Coming to the first ingredient in the FPGA, which is SLICEL, L refers to the logic. If you look at the picture, the first thing present over here is a 6-input LUT. This 6-input LUT is made up of 2 5-input LUTs, and you can combine 2 6-input LUTs by using these multiplexers present in between to make another 7-input LUT. And similarly, by using this 7-input LUT and then this 7-input LUT, you can make another 8-input LUT. Suppose if there is carry after one operation, if we pass through it through general routing, it will take more time. So to reduce the propagation delay, Xilinx has put this carry chain where there is a dedicated hardware routing of the carry, and then we have the flip-flops. Whenever you use the register data type in the Verilog, then these flip-flops in the hardware will be activated. Now let us see the SLICEL in the hardware. If we run this TCL command, which refers to tool command language in the Vivado, if you see the floor planning of the Zynq SoC, this part is nothing but the PS, and this part is nothing but the PL part. And the PL part is divided into 6 regions depending on the clock regions as X0, Y0, X1, Y0 and so on. By using the TCL command, let us see where the SLICEL are located in the PL part. If you zoom in, all the parts which are colored in green are the SLICELs. If you see, one more interesting part is all the SLICELs are arranged in the columnar fashion, which exactly resembles the ASMBL architecture, Advanced Silicon Modular Block Architecture. And you can see in some places two slices are together. If we zoom in, then we can see the LUTs, muxes, carry chain and the flip-flops which we have discussed earlier. We can also see a similar kind of slice which is similar to the SLICEL, and if you run the second command, then you will get to know how many SLICEL are present in the PL part. So you can see there are 8950 SLICELs present totally in this chip, and SLICEL and SLICEL, two SLICELs combined together is known as a configurable logic block. If you see the Vivado, in some places the SLICEL with separation between two consecutive SLICELs, but whereas in some places you can see two SLICELs are present together. So these two SLICELs are known as a CLB. If I hover my cursor, you can see at the tile it is CLB LL, which refers to a configurable logic block which is made up of two SLICELs. Coming to the next ingredient, we have SLICEM. Here M refers to the memory. If you look at the SLICEL and the SLICEM, the only difference you can see is the number of inputs present at the LUTs, and the rest all is same. In the SLICEL, where you cannot change the SRAM bits once the FPGA is programmed. On the other hand, in the SLICEM, you can dynamically change the SRAM bits present in the LUTs. And a 5-input LUT can be used as a 32-bit RAM. Similarly, a 6-input LUT can be used as 64-bit RAM. And then by using multiplexers, you can combine two LUTs and then use it as 128-bit RAM and subsequently as 256-bit RAM. SLICEM is similar to the SLICEL but with the additional property which can be also used as RAM, and this RAM is known as distributed RAM. We can also use the SLICEM as shift registers. The shift registers can be used to delay the inputs. Let us see the SLICEM in the Vivado. If you see, whatever the gap it was present before beside the SLICEL, so they are nothing but the SLICEM. If I hover my cursor, here you can see type is SLICEM and the tile is CLB, which is nothing but a configurable logic block. And you can see previously it was LL and here it is LM. Here LM refers to a CLB which is having a SLICEL and then a SLICEM. If it is LL, the CLB is having SLICEL and then SLICEL. If I zoom out, here you can see all the SLICEMs are arranged in a columnar fashion, which exactly resembles the ASMBL architecture. And if you look at the number of SLICEMs present in the FPGA, it is 4350. Due to the memory property of the SLICEM, SLICEM is more complex to build than the SLICEL. The SLICEM and SLICEL is also known as a configurable logic block. Here you can see there are total 13,300 slices. Out of them, we are having CLB, which contains L plus M, are 4,350, and the CLBs which contain L and L are 4,600. So together there are 6,650 CLBs. And here my question is, we saw slice L and L and L and M, but why there are no M and M? Whatever you are seeing, these are nothing but the switch box routing. In order to communicate between different CLBs and different ingredients in the FPGA, we will be having these switch boxes which help in the communication between them. You can see the number of routing is increased in the SLICEM case than the SLICEL. To make the switch box for the SLICEM, it's more complex. So if you have two SLICEMs together, then it will be very complex to design the corresponding switch box. Coming to the next ingredient, DSP48. DSP refers to digital signal processing, and in the signal processing applications we require a lot of multiply and accumulate unit, which is what exactly this DSP block does. It is having a dedicated hardware block which helps in the multiplication. Suppose if I want to multiply large number of bits together, if I use the carry chains, then it would take up a lot of CLB resources. Instead of that, I can use the DSP block to do it. Here, unfortunately, we cannot see what is present inside the DSP, but we can look at the high level diagram of the DSP48 to know what happens inside it. It is having a pre-adder, which is very much useful in case of FIR filters because FIR filter has symmetric coefficients. Here you can see it is having a 25 cross 18 2's complement multiplier, and then we are having registers to store it, and it also has ALU unit pattern detector. After getting the output from the multiplication, we can compare it with the pattern, and if you look at the output is again fed back to this multiplexer, and this can be used as accumulator unit. By using the DSP, we can implement the MAC operations very efficiently. If you run the TCL command to find the DSPs, even here the DSPs are arranged in the columnar fashion. In the each clock region, each column, you'll be having 20 DSPs. Overall, you'll be having 220 DSP slices. Coming to the next ingredient, memory, FPGA has dedicated block RAMs. Each BRAM can store up to 36 kilobits. Here B refers to bits, not bytes. So a single BRAM can be used as 36 kilobits individually or two 18 kilobits of RAM. We can also use the BRAM as a 36 kilobit ROM, which is read-only memory, or else we can also use it as RAM, where you can dynamically change the bits present in the memory. You can also use it as simple dual port RAM, where you will be having two ports. One port is for reading and another port for writing. You can also use it as true dual port, where you have two ports and each port you can do read or write, and similarly for the second port as well. And each port has the corresponding clock. You can read and write simultaneously, and that too at different clock speed. We can do it in 36 kilobits or 18 kilobits. Another way which we can use BRAM is FIFO. FIFO is first in and first out. Suppose we are having a sensor which is sending the messages at 100 megahertz. I have the processor which is working at 50 megahertz. The processor may miss some of the data which the sensor may send. So in that case, we can send the data of the sensor to the FIFO. So these FIFOs can be used as buffers. And from the FIFO, we can get the readings to the microprocessor. The BRAM can be used as 36 KB FIFO or 18 kilobyte FIFO. We can also use the BRAM as cascaded deeper memory. We can combine multiple BRAMs together and then we can make a large memory. If you use these TCL commands, then you can see even the BRAMs are arranged in the columnar fashion, and in the each clock region, each column you have 10 BRAMs. Total you have 140 BRAMs in the FPGA. In the further videos, let us look at the other ingredients of the FPGA and also how the Verilog code is mapped to the hardware. If you find this video helpful, please like this video and also share it with your friends, those who always do the Verilog but don't know what is present in the hardware.